Good morning friends. As you know that we are about to conclude this lecture series on classical control theory. So this particular lecture is in continuation with the previous one, which was based on theory of controller. In this particular session, we will see the concepts of phase lead compensators in detail. We'll start with the pole zero requirements of the phase lead compensators. Then we will see how to realize a phase lead compensators with the help of passive elements. By saying passive element, I mean the circuit will consist only capacitor, resistor or inductor types of elements. There will not be any elements which require any additional power supply when operated on. The example of active network will be one which consists of elements like operational amplifier. So in this particular session we will just talk about passive networks to realize phase lead compensators. After realizing phase lead compensators, we will try to analyze the phase lead with the help of board diagram of this network. We will see and we will derive and calculate also at what frequency the phase lead is maximum and what is the value of this particular given phase lead for that frequency. So without further ado, let us switch over to PowerPoint.
We know that by the term frequency response, we mean the steady state response of a system to a sinusoidal input. So we are having a given system with a transfer function Gs, an input signal xt, and output signal yt. So what does this definition mean? It means that if xt is equal to x sine omega t, then the output we have already derived, steady state output YSS, is given by capital Y. Capital Y is the amplitude of that particular sinusoidal signal. The steady state output will also be sinusoidal in nature with amplitude Y and with the same frequency omega t, but with a change phase phi, where we have already calculated that y is given by magnitude amplitude of original signal multiplied by magnitude of sinusoidal transfer function at the given frequency. This frequency omega is basically frequency of the signal. Similarly, phase phi, we already calculated that nothing but the angle of sinusoidal transfer function with a frequency omega. Now, while designing lead compensator in the previous class, I said that it is the sinusoidal input which decides whether a compensator is lead compensator or lag compensator or lead lag compensator. So, in this particular case, we want our compensator to lead the output. So, if phi is positive, then we say that there is a phase lead. So we want a transfer function of compensator. Say I am going to say GC j omega is the transfer function, sinusoidal transfer function of the compensator. We want GC j omega or correspondingly GCS such that this phi is positive. What should we do in this particular case? So in very simple case, you can imagine that let us take GC is equal to 1 plus s. What will happen in this particular case to this GCJ omega? So GCJ omega will be equal to 1 plus j omega. And then what will be the corresponding phi, which we are claiming to be positive? So it will become tan inverse omega by 1, right? Now, since omega is a positive quantity as it is frequency, and this 1 is already positive, so whole this tan inverse, because tan inverse is an increasing function, it will give positive value for positive argument, and this argument is positive, that's why phi will also be positive. So it seems that 1 plus s will provide us a simple phase lead, and we can design, if you'll have some component which will provide a transfer function of something like 1 plus s, then we say that we are having a phase lead compensator. Now, since an isolated zero is not physically realizable, we must add a pole along with the compensating zero so as to achieve physical realizability. This pole, of course, be added far away from the j omega axis such that it has negligible effect on the overall behavior of the system, and hence will have such pole zero configuration. So note that here we wanted just a zero to be included in our transfer function, but since isolated zero is not possible, that's why we have taken a pole, but the pole is far away from the j omega axis. See, closer the pole to the j omega axis, more prominent is the effect of the pole on the overall behavior of the system. That's why we want that the behavior of the system to be dominated by this zero only, and that is why we want the effect of this pole to be negligible on the overall behavior of the system, and so we taken this pole far away from the j omega axis. Since we just wanted this 0 to be here and this pole is unwanted, but due to physical realizability we have taken this pole also. So our overall transfer function of this particular compensator becomes something like gs is equal to s plus zc divided by s plus pc, where we say that this is basically at minus zc as a 0, and this is basically a pc, which is pole. So this seems to be a general form of transfer function for lead compensator, but it is having one more suitable representation. We say that gc is equal to this whole term, and that is equal to s plus 1 upon tau divided by s plus 1 upon alpha tau, where we say that tau is a positive quantity, tau greater than 0, and alpha, that will be equal to zc by pc, and that is less than 1. Since alpha less than 1, so this pole will be far away from this j omega axis, and hence we can say that minus zc will be equal to minus 1 upon tau, and minus pc will be equal to minus 1 upon alpha tau. Alpha is less than 1, so 1 by alpha will be greater than 1. So 1 upon alpha tau in magnitude form will be greater than 1 upon tau. Since it is negative, so it will be far away from j omega axis in negative side. Okay, so now further simplifying this whole term, we'll have GCS will be equal to alpha tau s plus 1 divided by alpha tau s plus 1. So this is basically a general transfer function for the lead network where alpha is less than 1, which is ratio of ZC upon PC. If you want to find the alpha, you will take the ratio. This is basically ZC, this is basically PC. If you take the ratio of ZC upon PC, you will automatically get alpha. And we have assumed that alpha is less than 1. The lead network can be realized by an electrical network which is shown here. It will look like this. Now we are having this electrical network, and I am claiming that this electrical network will behave like lead network. So let us try to prove it. So say this is your input signal EI, and this is of course function of time t, and this is your output signal EO, also a function of time t. And if you will convert this whole circuit in Laplace domain, this will become EOS. You know that we take the capital letter for frequency domain, and this will become EIS. R1 will remain as such, R2 will remain as such, and C in frequency domain will become 1 upon SC. So here this whole term, this will behave like that. We are having two register. One is having value R1 and another one is having value 1 upon SC, and they are connected in parallel. So equivalently, we will have EOS. If you will try to derive this simple equation, then you will get EOS upon EIS, which is the transfer function of this particular circuit, will be given by R2 divided by R2 plus R1 upon SC divided by R1 plus 1 upon SC. This whole term. This whole term is basically signifies the parallel combination of this C and this R1, or equivalently you can say 1 upon SC and R1 are in parallel. So if you will try to derive the equivalent resistance, you will get 1 upon RC multiplied by R1, this term, divided by R1 plus 1 upon SC. And this resistor, the equivalent of this resistor, is in series with R1, R2. Clear? So it is in series with R2. So if we will take this EI term this side, so what will become? EI upon this whole resistance term will become current, and multiplied by this R2 will become voltage, output voltage. So I have just rearranged this term to get the transfer function directly. So let us rearrange a little bit. So I'll have EOS upon EIS, that will given by S plus 1 upon R1C divided by this whole term will be divided by S plus 1 upon this R2 divided by R1 plus R2 multiplied by R1C. And now, if you will compare this particular equation with our original equation, what was our original equation? Original equation was S plus 1 upon tau divided by S plus 1 upon alpha tau. This was basically, we said that this is the general equation for a lead network, and further we said that this particular circuit can be used to realize this lead network. And when we try to prove or try to derive the transfer function, and after little bit of rearrangement, we get something like this whole jumble thing. And if we try to compare these terms, uh, this particular transfer function of this particular given circuit with a general form of lead network, we will conclude that tau will be equal to R1C for this particular given network, and alpha will be equal to R2 divided by R1 plus R2. It will be better if you will remember these two results. It will be more helpful for you. How can you remember? See, R1C. So here these things, this resistor is in parallel with C, that is why R1C. And alpha, we claimed that alpha is less than 1, then only it will act as a lead network. And see here, alpha is a ratio of R2 upon R1 plus R2, and it will be of course less than 1, and hence this particular circuit will act as a lead network. Now we were having transfer function, general transfer function rearranged uh, like alpha multiplied by tau s plus 1 divided by alpha tau s plus 1. This was the general transfer function for a lead network. And now we want to consider sinusoidal transfer function. You know that how can you consider the sinusoidal transfer function? You will put s is equal to j omega in the transfer function. So this sinusoidal transfer function will become gc j omega is equal to alpha multiplied by, I am taking this one term beforehand, so j omega tau divided by 1 plus j omega alpha tau, and of course alpha less than 1. Note that at zero frequency the network has a gain of alpha. At zero frequency means if you put omega is equal to 0 in this particular equation, this gain will be, this whole term will vanish, this term will become 0, this term will become 0, and we will have just alpha, and alpha will be gain. Clear? So at zero frequency the network has a gain of alpha, and alpha is less than 1, or we can say instead of gain we can the inverse of gain is basically attenuation. So we can say at zero frequency the network is a gain of alpha, or in other words an attenuation of 1 upon alpha. And since 1 upon alpha is an attenuation at zero frequency, and we know that DC signal is having frequency 0, so we'll say that this is basically attenuation, DC attenuation. So in frequency domain compensation technique, it is convenient to cancel the DC attenuation of the network with an amplification that is equal to alpha is equal to A is equal to 1 upon alpha. If you will take another amplification combined with this given lead network circuit, then we can cancel this gain alpha. And the lead compensator is then can be visualized something like this. Clear? So we are having the same circuit. Here it is R1 and here it is C, here it is R2, and there was a alpha term appearing in the transfer function of this system. So we have taken an amplifier having a gain of 1 upon alpha. So what we will get? So finally, after considering the gain of 1 upon alpha to cancel out the DC gain of the original lead network, we will say that our final sinusoidal transfer function of lead compensation will look like this. GC equal to J omega, that is equal to 1 plus J omega tau divided by 1 plus J alpha omega tau, where alpha is less than 1. So this will become our final transfer function after consideration of this block of gain 1 upon alpha. Now if you try to calculate the effect of angle, say I'm going to say angle is a phi, and phi is given by basically J omega. So what it will be? It will be tan inverse omega tau, this numerator, and this denominator will give negative angle, tan inverse alpha omega tau. And if this positive term will be greater than that of negative term, then only we will say that phi is positive. And since alpha is less than 1, here a constant is there, we have already assumed that alpha is less than 1, the argument of this second tangent, inverse tangent, will be lesser than that of argument of this first tangent, inverse tangent term. And that is why this term will be greater than this one, and overall phi will become positive, and hence we can say that this is also a lead network. Now, after removing the term alpha with a amplification of 1 upon alpha, finally we are having the transfer function of lead network is something like this. So now if you will try to draw a board diagram for this, how you will approach? So first we draw the amplitude plot and then we draw the phase plot for this. Why we want to draw amplitude and phase plot? So that we can analyze how this system behaves with respect to the change in frequency. So first thing, or the first step in case of board diagram, is that to find the corner frequency. Since we are already having the transfer function represented in terms of sinusoidal transfer function, because as we have already put S is equal to J omega, so we are having this transfer function, and we want to find the corner frequency in this sinusoidal transfer function term. So the corner frequency, as we know, from the numerator will have 1 upon tau, and from the denominator will have 1 upon alpha tau. So we'll have two corner frequencies. We want to draw basically approximated plot. We know that at corner frequency the error is maximum, and which is equal to 3 dB in magnitude. So if we'll try to plot it, it will look something like this. So here we are having one corner frequency 1 upon tau. Basically this is tau. Okay. So 1 upon tau, and second is 1 upon alpha tau, and following the basics rule of the to draw the board plot, you will have some board plot like this. And here, since it is written in omega, but basically it is in log base 10 omega. We already know this, right? Because we are assuming that this has been drawn on semi-log graph sheet. So on semi-log graph sheet, you take the value or of omega, but it automatically is the value for log of omega with base 10, unless until I specify that you have to take the base 2. Clear? So in terms of decade, it is in base 10. Well, now we want to draw the phase plot. For phase plot, you have to make the table and you have to take the corresponding angle with respect to frequency, one side frequency and one side angle. So if you will draw this plot, it will look something like this. But for the time being, we don't know, assume that we don't know what is omega m, which is the maximum, which is the frequency basically at which this phase lag is basically phi and phase lag is maximum. So what is the frequency at which this phase lag is maximum? We don't know right now. Clear? And we want to calculate it. This is basically aligned with the board magnitude plot. So this is basically alpha tau. This is 1 upon tau, and once again also it is in log omega. We have taken here just magnitude in decibel. Clear? And this is angle in degree. You know that. Okay. So we want to find the value of frequency at which the phase achieves maximum value. How can we find this? Well, so first we will find the value of phi in terms of omega, and then we will differentiate that value of phi with respect to omega and put that differentiation equal to 0. Then it will automatically give us either minima or maxima, and then uh, performing the second differentiation will find that no, it is basically maxima in this particular case, not minima. Clear? So first write the equation for phi. We have already written previously also. So phi will be equal to, according to this equation, so this is j omega tau, so tan inverse j omega tau divided by 1, that will be equal to tan inverse omega tau, means imaginary part divided by real part, and the denominator is basically alpha omega tau. So imaginary part is alpha omega tau divided by 1. So it will become tan inverse alpha omega tau divided by 1. Okay. So what we'll perform basically d phi upon d omega. So what is the differentiation of tan inverse x? Well, so this will become d of tan inverse of omega tau divided by d omega minus tan inverse, means differentiation of tan inverse alpha omega tau divided by d omega. Further simplifying, this will become 1, it will basically tau upon 1 plus omega square tau square, this is square. Clear? Minus alpha tau divided by 1 plus alpha square tau square omega square, right? And that you will put equal to 0. So if you put that is equal to 0, so you will get omega square is equal to 1 divided by alpha tau square, and hence you will have omega that is given by 1 upon tau root alpha. Okay, so this, now we have just verified this claim. So this, at this frequency omega that is equal to 1 upon tau root alpha, the value of phase will be maximum. What is special? What is symmetricity about this? If you rewrite this omega, you can rewrite this particular value 1 upon tau root alpha as something like this. I'm just taking this tau inside and rearranging. So 1 upon tau multiplied by 1 upon alpha tau. Clear or not? If you will take this tau outside, so it will become inside the root square root, it is tau square, so you can take that tau outside and it will once again become 1 upon tau root alpha. But we have expressed this particular equation in this special form to show you one of the point. 1 upon tau is what? This corner frequency. 1 upon alpha tau is what? This corner frequency. So without deriving or without performing this whole derivation for minima and maxima, if you are able to find the corner frequency, and corner frequency you can very easily find with the help of the given transfer function of a lead network, you will be directly able to find this omega m, because you can remember this omega max as geometrical mean of these two corner frequency, right? This is basically geometrical mean of these two corner frequency. Either remember this formula or just remember that at omega is equal to omega m, which will be equal to the geometrical mean of these two corner frequency. The value will be, the value of phi will be maximum. See, it is a peak. It is a maximum phase lead you will get at this frequency. Clear? Well, so we have just calculated that maximum phase lead, or the maximum value of phi, which is equal to phi m, is possible at this value of frequency. Omega m is equal to 1 upon tau root alpha. But what is the value of phi m? We want to calculate the value of phi m. For that, first recall that original equation of phi. Phi was basically equal to tan inverse omega tau minus tan inverse alpha omega tau. Let us rearrange it. Tan inverse A minus tan inverse B in the form of that, and write in terms of tan phi. So tan phi will be equal to what? This omega tau multiplied by 1 minus alpha divided by 1 plus alpha omega square tau square. Just, if you can't recall it, go and revise your trigonometry. So you will get finally this value, and we want the value of phi m. So conversely, you can also write this formula as if phi is equal to tan inverse this omega tau 1 minus alpha divided by 1 plus alpha omega square tau square. And if you put omega is equal to 1 divided by tau root alpha, then this value of phi will become phi m. So put this value of omega in equation, and then finally you will get that value is given by phi m will be given by it will become very nice equation, 1 minus alpha divided by 2 root alpha. Or you can just either tan inverse of this, since I have already given equal sign, so there is no space. So we can also write tan phi m. Tan phi m will be given by this one. If you know the value of tan, you can also calculate the value of sine. So accordingly, sine phi m will be given by, this is more nice, 1 minus alpha divided by 1 plus alpha. So I used to remember while appearing for examination, I used to remember this equation for maximum phi m. So sine 1. So if you know that sine phi m is what, you will be able to convert it into in terms of tan phi m, right? That right angle triangle and perpendicular by base or perpendicular by hypotenuse, right? It was a rule, na? Rule is the what? What was that rule? Can you recall that? P by H, right? Perpendicular by hypotenuse. This if this is phi and this is perpendicular and this is hypotenuse, so perpendicular and hypotenuse, and then finally you will be able to find the value of tan phi. And if you will rearrange once again this whole term, there it is plus, right? Don't be confused. So you can also conversely find the value of alpha. So alpha, if you with the help of this equation, alpha will be equal to, once again it will be a nice form here, 1 minus alpha, and it will become 1 minus sine phi m divided by 1 plus sine phi m, right? So either remember this, the above formula, or this one. Better to remember this formula only, and you can rearrange. Means 1 plus, then here also 1 minus 1, or 1 minus sine alpha, you will get 1 minus this term, and after a little bit of rearrangement, componendo and dividendo, you will be able to get whole this term. Clear? So we have just calculated this omega m, then finally phi m in terms of by putting value of omega m, omega is equal to omega m. Also calculated the formula for sine phi m, that is equal to 1 minus alpha divided by 1 plus alpha, and once again represented this formula into the in terms of alpha, and alpha was 1 minus sine phi m divided by 1 plus sine phi m. But now we want to find what will be the value of magnitude here at this particular frequency. What will be the value of magnitude at this particular frequency? So what we'll do, we are having magnitude is equal to what in general term? The GC was equal to GC j omega was equal to what? And this one 1 plus j omega tau divided by 1 plus j alpha omega tau. This was basically the sinusoidal transfer function for lead network. And now we want to find the magnitude of this. So this magnitude will be equal to this one. And you are interested in finding magnitude at which frequency? At the frequency at which the angle phi is maximum, and that frequency was omega m, which was equal to 1 divided by tau root alpha. So replace every value of omega by 1 divided by tau root alpha. So what you will get? You will get GC j, I am going to say this is at frequency omega, so I am going to say omega m. Magnitude will be given by, after solving, you will get a very nice formula, and that will be equal to 1 upon root alpha. All these formula are important for both semester examination or IES examination or even GATE examination, right? So GC will get 1 upon root alpha. And if you will take the log of this, because here the things are in decibel, so if you will take 20 log of this, so it will become this value. Clear? Right? What if you want to find the value of at this, at frequency this one, 1 upon alpha t? What will do? Just instead of omega m is equal to 1 upon tau root alpha, you will put omega is equal to 1 upon alpha tau in this value of omega. Then you will get uh, gc j omega. At this value of omega, you will get 1 upon alpha. So, and you know that from the rule that this will be basically constant afterwards. This is basically approximated curve. If you look at the real curve, it will be somewhat smooth here, right? And here somewhat uh, smooth here. Okay, and this maximum error is, you know that this is 3 dB. Clear? So before we end this lecture, I would like to highlight two more points. Number one is that for phase lead greater than 60 degree, it is advisable to use two cascaded lead network with moderate value of alpha rather than a single lead network with two small values of alpha. You know that you can, if you want a particular phase lead alpha, so you are having a formula alpha is equal to 1 minus sine phi m divided by 1 plus sine phi m. So accordingly, for a given value of phi m, if you want a particular phase lead, you can adjust the value of alpha, right? And accordingly you can adjust the transfer function. But uh, means for phase lead greater than 60 degree, instead of one lead network, it is better to use two lead networks with moderate value of alpha. And second point, I want to highlight that let us focus on this particular board magnitude plot of this lead network. Uh, See that in this diagram the frequency is increasing. So at higher frequency we are having a gain at very high frequency, more than that of 1 upon alpha tau. The this become constant value, the amplification become constant, and that is equal to 1 upon alpha. If you will take represent it in terms of dB, it will become 20 log with base 10 1 upon alpha. Basically in terms of just gain, it is 1 upon alpha. So at higher frequency the gain is 1 upon alpha, this value, and at lower frequency it is 0 dB, means and the gain is basically means you are having very high gain at you are having a gain of 1 upon alpha at higher frequency, and you are having no any gain at a corner at some value of frequency which is less than second corner, means first corner frequency, that was equal to 1 upon tau. So the thing is that we can conclude that the nature of basically inherent noise in control system is such that the noise signal frequency are higher than the control signal frequency. We know that if somebody is going to tell you about noise, so noise are basically uh, a higher frequency signal. So this board plot clearly represent that in case of lead network, the high frequency noise signals are amplified by a factor 1 upon alpha. So alpha was less than 1, so 1 upon alpha was greater than 1. So noise is going to be amplified in these regions. So noise frequency will lie are always higher, so it is expected to be higher than that of 1 upon alpha tau. So will now noise frequency will lie in this region, and in this region the gain is basically 1 upon alpha, and alpha is less than 1, so 1 upon alpha will be greater than 1. So the noise frequency will be the noise signal will be basically amplified, right? While the low frequency signal, which is basically the control signals, undergo undergo unit amplification. So there is no, because it is 0 dB, so you can say that the amplification factor is 1, so it will remain as such. So the control signal will remain as such because control signal is basically a low frequency signal, and the gain in low frequency is basically 1, and in terms of dB it is 0 dB, while the gain in higher frequency is basically 1 upon alpha, which is a value greater than 1, because alpha was less than 1, so this value greater than 1. So noise frequency is going to be amplified by a value 1 upon alpha, while signal frequency will remain same. Clear? So when we will talk in terms of communication, we are more concerned about signal to noise ratio. We should we signal to noise ratio, we need to improve the value of signal to noise ratio, right? So in this particular case, means in case of lead network, basically signal to noise ratio at the output of the lead compensator is poorer than the value at input. So when the signal will pass through the lead network, the signal to noise ratio basically deteriorate, which is one of the disadvantages, you can say. Okay, so in the next class we will talk about lag network, which is similar to this one. Thank you for listening.